Hello, my fellow believer, and I call you that because if you've worked on this problem, you know that the devil exists. And I don't think you're just randomly clicking on this video. So why is this problem so complicated? Why is it so difficult? Why is it that you've watched the 30, 40, 50, 60-minute videos? You can maybe remember the solution, but you don't understand it. And more importantly, you wouldn't be able to derive it yourself originally. Like, what is it that's so difficult? Well, that's what I want to go into. I want to explain this in a way that you can remember it more easily. You can think, so you could have arrived at the solution by this sort of thought process in the first place. And I want to just generally explain why it is difficult to understand. And the reason it's so difficult to understand is because it isn't just one problem. You have the problem statement on the left. Pause it right now if you're not familiar. You should be. But the final problem is many problems. Whenever we talk about finding a median in the original problem statement, that's just one part of our whole problem. But that in itself is a problem. That's why you get stuck. Because, as I've drawn in this page here, there are multiple problems in this one problem. On the top right, you'll see the key circle is a problem, square is a solution or an idea. So we start essentially in Leetcode. This image represents the problem that they give us and say, yeah, go do this. This is a normal thing to ask someone to do. So the visual representation of our problem is we have a final joined array, like virtually we need to find the middle of this, whatever the final joined array will be. And that middle or median could be anywhere in these child n1, n2 arrays, nums1, nums2. That is multiple problems, and this is the problem. That's why it's difficult to understand. So in problem solving, you need to, if you have a complex problem, you need to break it down, not meaning, boogie, but split it into parts. The same way if you were reading a paragraph in French, which has 40 French words, unique words, but you only understand 4 of them, you are going to need to take the other 36 words and for each one say, what does this mean? And only once you've internalized the other 36 unknown words, you've split the paragraph into pieces, only then can you go back to the paragraph and read it through as a whole and understand what the hell is going on. So how do we split this final problem? Let's imagine we're starting at the end of a chain of problems that have gotten more and more and more complex. What is a slightly simpler version of this problem? So for finding and deciding where the middle is, and the middle could be anywhere, well, what if we just need to decide what the middle is if we know for sure it's in n1 or n2? Oh, so now we don't need to find. We just need to decide or get the middle from a certain place. That's a bit simpler. There's 1, 2, 3 less things we need to do there. But could we go even further? Like, what would be the step before this? It would be saying, rather than getting the middle or the median out of 2 arrays, when you split them, you know for sure it's at their middle somewhere. How do we even get the middle? What's a median middle? The median is that in a single array, it's just the exact middle. But then there's more problems. What a surprise. That's life, guys. Don't look forward to getting older, basically. To get the middle is 2 problems. So you're up here, you're on Leetcode thinking, oh my god, how do you do this? It's because you haven't even internalized or set out how to even get the middle of a single array. Because even that has 2 different cases that you have to solve and remember. We can split this basic ass problem into 2 other problems. So now we have 3 problems just for the simplest bit at the very beginning. How do we get the middle of an odd array? Okay. How do we do that? You have the number 1 to 9. Divide that by 2, round down, you get the number 4. 9 divided by 2, 4.5, round down is 4. That's an index. Again, this is another thing you need to keep track of. The 4th index is going to be the middle, which will be the 5th value, like there's an off by 1 there. And whenever you do get to this middle point, you have 4 on either side of it. So for an odd array, you now know the solution. Oh, you just divide by 2, round down, and there you go. If you imagine now that this is an array that we've picked, we're at the very end of it. So we'll actually just take the one that we've divided by 2 to get. But if we go back up to this problem, get the middle. Okay, now let's go down the children nodes again. Another problem, even. Okay, in this case, the array's length is 10. You divide by 2, and it takes you to the number 5. If we're using the index the way we were here, so remember we divided by 2, the length of 8 divided by 2 gave us 4. That was correct, because in an odd array there's 1 extra. So you have the left side, and then you have like this extra 1 at the 4th index, which is really the 5th value. But if you do this same logic in an even array, you do 10 divided by 2 to get the index, it'll give you the index of 5, which is actually the 2nd middle. So you do your division to get to here, but then you want to go 1 step backwards as well. So to get the middle of an even array, you want to divide it by 2 and then adjust it down by 1 to get the first middle. And then you want to keep the original divide by 2 for the 2nd middle. And then when you know both of the middles, you add them together and divide by 2. You get the average. That's the way you do that. So now we know, okay, this is how I get median for a single array, for an odd and an even. And you can see, why is this problem so difficult to solve? It's because you're doing many, many sub-problems, but you're not clear that you need to do them or that you are doing them. They're just sort of in your head vaguely, or you don't even know that this thing needs done. So now that we know to get the middle, we have to decide, okay, next level of this problem is, we know how to get the middle, so we're going to go to the middle the same way we did previously, but we're going to do it for 2 different arrays simultaneously. How do we choose or get the middles whenever the final array is odd? Okay, so for the n1 and the n2 array, we're using the logic that we did here, the divide by 2 logic, to get to this middle point. We're doing that on both of them. So we've reached this section with our 2 pointers here. So this and this. So now what we do is we take the biggest of the 2, because if you're going for the middle and you have a left side and a right side, and your middle is on the left, because in odd arrays, remember from this division, whenever you pick a middle, you could imagine that that's part of the left. The left is going to be bigger. It's 4 plus 1. So whenever we're over here, you want to take the biggest because that's the closest to the middle. Obviously you take the biggest because if we are picking these 2 values, and that was 3, you want the 5 because it's the biggest, which is the middle. Okay, so now we know how to get the middle, or decide which is the middle, whenever we know where the middle is, for an odd array. How do we do it for an even? Okay, well, similar to how we did it for a single array, we need 2 middles. So this time we have our left middle, M1, and our right middle, M2. The same way over here, we had the M1 and M2. We do the same as we did for the odd array, where we get the biggest on the left. And now this time we also pick the smallest on the right, because we want the closest to the middle. So that is now how you decide if we have the middle for sure in n1 or n2 at their middle, how do we get the correct median? So we've solved two simpler problems from this original big, huge problem. And now we could sort of start hoping to attempt breaking down the massive problem, which is the extra step now of also finding and deciding which is the middle. So now we know how to get the median. We know how to pick the median once we're definitely there. How do we know if we're there? When do we need to find? This is another problem, is when do we need to go look for the middle? And we do that whenever something on the left is bigger than something on the right. Why is that? Because in a sorted array, the left side is always smaller than the right. So if we are making up a left from nums1 and nums2, and we're making up a right from nums1 and nums2, clearly everything in the left needs to be less than the right, because that's how ascending order works. Okay, so we know we need to go find the middle whenever these logical conditions are not true, whenever the n1 left is bigger than the n2 right, and then the other for this, so I can't be bothered saying. Whenever that logical condition is not true, that's when we go look for the middle. Next problem, let's break it down into the odd and even of how do we find, how do you go find the middle? So let's imagine we're just starting at the middles of the two arrays. That's our indexes that we've picked randomly. This logical check has failed, so we know we're not at the middle. How do you go look for it? Well, you could just step backwards or forwards. If the value is too big, you could go left. If it's too small, go right. And that's a perfectly okay solution. This is a solution box. If this is the wrong value, you just go back one. And then based on this is another problem. I didn't have space to draw it out. But if you move back on the left, the total size of the left now might be wrong. So let's say the final joined array's left side is 10 elements. If you move this back, it will now be 9 elements unless you also shift this one and make this side bigger. So whenever you are looking in one array for the answer, you need to also just adjust the sides of the other to keep the left side and the right side of the final joined array equal to what it should be. That's another subproblem. You could draw out another node for that. So let's imagine we have that in our heads now. The next problem is the finding doesn't meet the full condition of the problem, which is to do it in a logarithmic time. So tilde, the find is too bloody slow. This is why it's slow, because that's what you're doing. You're hopping one at a time to the left and doing the same in the other n2 array. The solution for that is a binary search, the visualization there where you jump half the array at the time. Now you kind of know what to do, but again this brings in more problems. Which array do you search? I suppose even if you just use indexes for one and you jump from point to point, you are kind of searching both, because you would automatically be adjusting the size of the other one based off the size of this one, because the left needs to always add up to some value. And ultimately, it doesn't really matter which side you pick to search, because, and I've put that as a problem here, which do we search? It doesn't really matter, because if you bounce through the shorter array and you don't find it, well, if you didn't find it in that array, then you immediately know that the middle is in the middle of the other one. And it's exactly the same for the bigger array. If you bounce through this, you don't find it, oh, now we can just immediately know it's in the middle of the other array. So basically, if an array is irrelevant, then you just look at the other one, the middle. So you can search either. You may as well do the smaller one. And then back to saying which pointers we use. Let's say we're searching the smaller one. This kind of relates to the earlier problem of keeping the sizes the same. So say we get to the middle point in our binary search, we're looking at the n1 array, and we're only getting one value. But let's say we need 10 elements from the total, like the left side, let's say it has like 10 elements or something. If you're only getting 1 from n2, then it would just be 10 minus 1 is 9. So then the n2 array would be up at 9, like the 9th index or whatever, or 9 values, so the 8th index. And you can see a calculation for that here. So zooming out, the key point is that there's multiple problems. The final problem can be split into preceding intermediate problems, and it's kind of like a tree or a graph. I quite like the question of what is this problem derived from? Like, imagine that we could take a step backwards. What is the simpler or the preceding step before it? And that's how you get to this and then this problem. So let's go and try and code it. And the other difficult thing about this is, as you code linearly, you're jumping from point to point in the graph. But anyway, we're going to do our search, our binary search, but we wanted to search the smaller array, so we will just say if nums1 is bigger than nums2, then we swap them around so that we keep our pointers consistent. We can get some extra informational variables like the total length, half the length, like what's required on the left side. Round down, that's what the double slash is. And then we can say, is it even? And there we have some helpful information for like what we need. We need to know what's the total size of the left, so we can, based on the n1 pointer, find the n2 size that it contributes, stuff like that. And we need to know, is it even or odd, for all of our decision points when we need to handle different cases. So now we need to do the binary search. So n1's left, just 0. N1's right pointer is the length of it, minus 1. We're going to get the last point, standard binary search logic. Set up a loop. And then we say the n1 middle is equal to the distance between the pointers divided by 2. Yeah, so you get the halfway point and then you adjust it. So that's standard binary search logic. And then we can say the n1's left contribution. So this is what so in this case here, the n1 array is contributing one element at the 0th index. So we say the n1 left contribution is equal to the index plus 1. Because of this, if we're at 0, we're clearly contributing 1, so you need to just offset it by 1. For the n2's middle, we don't do this with separate pointers. We can just base it off what is the required contribution. So we say half of the final array's left. So sorry, the halfway, so say the final joined array is length 10, then half is 5. And if the n1 is contributing 1, then we're going to need to get 4. So we can say half minus n1 left contribution. However, if the array is even, there's 2 middles, and remember, whenever you divide by half, you're going to be 1 to the right. So if we're just dividing down to the half, we're going to be getting the m2. So we want to adjust back by 1 for an even array. That's why having sort of a map of problems and subproblems is quite helpful for this problem, because whenever you need to do something like get a middle, then you can go down this path like a tree and see, oh yeah, the solution for this is this. So n2m minus equal 1 if it's even. Now what we need to do is we need to, as part of our binary search, compare the values, because we only search whenever things are, like, we need to see if things are valid and if we need to keep finding things. So the core logic of our binary search is, well, when do we find things and is it valid? And when do we find stuff? Well, we need to do it whenever the comparison here fails. So we make the values for the comparison. So we have the n1 left value and the n2 left value, and the corresponding ones for the other side. So n1 left value, I'll just type it out. Okay, now here's the thing we hadn't discussed in the chart. If you go out of bounds on the left, then you want not an index out of bounds error, but a comparison to still show you that it's valid. And if we go all the way here and we're outside of the array, but you still want the less than comparison to be true here, well, you would want to set this element to be as small as possible so it always succeeds this less than 5 comparison. So we can set -infinity as our default value if the indices are out of range. So let's get the n1 right value now. We just do the same index plus 1. And in this case, we set it to the maximum value possible, because if we go out of bounds here, you always want this thing to be bigger than this one. Now we can do the same for n2, the lower array. Oh yes, it is. Copy paste is working now. So I will just fix up the indexes here. Make sure I'm using, so nums1 because I always mistype these. And then we have nums2 plus 1, okay. So what do we do now? We say if n1's left is less than n2's right, if n1 left val is less than or equal to n2's right val, and n2's left val is less than n1's right val, then it's valid, else it isn't. And in the case when it isn't, that is whenever we want to go do binary search, like this here. And how do you do that? You adjust the middle. So if n1 L val is bigger than n2 R val, so if this is too big, you want to go this way to get a smaller one. So if this was our right pointer here, you want to move that to here, so we then get rid of some of the bigger elements and our new middle becomes where I'm pointing at here. So if the n1's left side is too big, we want to adjust the right pointer, set it to the middle, -1, so we go back and we cut off some big elements. Otherwise, we just kind of do the opposite with the left pointer, we move it up. Okay, so what we're nearly done. What we've done now is implement the logic for quite a few of these boxes, but what we still have to do is this logic here when we kind of pick or decide the middle. So we know in this if statement that we've got a valid, like we're definitely at the middle. This problem handled that for us. It said, okay, you're definitely here or here at the middle, you definitely have it. Now we need to say, okay, let's get it. So if it's even, then like we said here, you want to pick the max from the left and the min from the right and divide by 2, as we figured out in the original subproblem. So we can return the average of the max of the left side plus the min of the right side. And that is, remember, because you want to get what's closest to the middle. And if it's odd, what do? From the left side, we just get the biggest because it's the closest to the middle. And I am going to collapse if there's a bunch of syntax errors, and that will... Oh my god, what have I done? That was your fault, person watching. Okay, so I had a couple bugs in the typo, like I was doing a minus infinite here and accidentally typed the wrong array here. But hopefully that clears up some of why this problem is difficult, and yeah, that's it. See you.